The densest objects in the universe are not black holes. They are smaller, quieter, and far stranger. When a massive star reaches the end of its life, gravity wins a final, overwhelming argument. The star collapses, matter is crushed beyond ordinary limits, and what remains is a neutron star, a sphere so dense that a single teaspoon would outweigh a mountain. Inside it, atoms no longer exist as we know them. Space between particles disappears. The familiar rules of matter begin to soften. If this quiet journey brings you even a moment of calm or wonder, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep these slow explorations alive, and I thank you for it. Now, let's begin with the first truth. Part 1. Part 1. When a star refuses to become a black hole. When a massive star explodes as a supernova, its outer layers are cast into space, but its core does something different. It collapses inward violently until gravity is balanced by a force that resists further compression. This balance point is not gentle. It is the birth of a neutron star, a remnant held up not by pressure from heat, but by the quantum resistance of matter itself. To understand what happens at its center, we must first understand why the collapse stops at all. For most of a star's life, gravity is patiently resisted. Deep in its core, nuclear fusion converts lighter elements into heavier ones, releasing energy that flows outward. This energy creates pressure, and that pressure pushes back against the star's own weight. For millions or billions of years, the balance holds. The star shines because gravity and pressure are locked in a quiet, ongoing negotiation. But this balance depends on fuel. When a massive star exhausts the lighter elements it can fuse, that outward pressure fades. Iron begins to accumulate in the core, and iron is a dead end for fusion. Fusing iron consumes energy instead of releasing it. In that moment, gravity finds no resistance left to argue with. The collapse begins silently at first, then it accelerates. The core, once held open by heat and radiation, starts falling inward at a significant fraction of the speed of light. Temperatures soar, densities climb beyond anything experienced during the star's long life. Atoms are squeezed closer and closer together until their familiar structures can no longer survive. Electrons, which once orbited atomic nuclei in spacious clouds, are forced into impossibly tight quarters. Under this pressure, they merge with protons in a process called electron capture. Each merger creates a neutron and releases a neutrino, a nearly massless particle that escapes almost instantly, carrying energy away into space. This flood of neutrinos is so intense that for a brief moment, the collapsing core outshines entire galaxies, though invisibly, in particles we barely detect. What remains after this transformation is no longer ordinary matter. The core becomes a dense assembly of neutrons, packed so tightly that there is almost no empty space between them. This is the moment the star refuses to become something else. The collapse does not continue forever. It halts at a boundary defined not by heat, but by quantum mechanics. This resisting force is known as neutron degeneracy pressure. It arises from one of the most fundamental rules in physics, the Pauli exclusion principle. This rule states that identical fermions, a class of particles that includes neutrons, cannot occupy the same quantum state at the same time. No matter how strong gravity becomes, it cannot force neutrons into complete overlap. They resist not by pushing outward in the way gas pressure does, but by simply refusing to be arranged any closer. This resistance is quiet and absolute. It does not depend on temperature. Even if the core cools, degeneracy pressure remains. It is a pressure born not of motion, but of identity. Each neutron asserts its existence by denying space to the others. When this quantum resistance matches the inward pull of gravity, the collapse stops. A neutron star is born. The rebound of the infalling material against this suddenly rigid core helps drive the supernova explosion itself, sending the star's outer layers outward in a luminous shell. The remnant left behind is small, dense, and extraordinarily stable, at least for now. To appreciate just how extreme this object is, it helps to slow down and consider scale. A A typical neutron star contains more mass than the Sun, yet is compressed into a sphere roughly the size of a city. If you could stand on its surface, gravity would be billions of times stronger than Earth's. A fall of just a few centimeters would release as much energy as a powerful explosion. Space and time themselves are noticeably curved there. Yet despite this violence, the neutron star is not chaotic. It is one of the most orderly objects in the universe. Every particle inside it exists under rules so strict they verge on absolute. Motion is limited, arrangement is constrained. The star becomes a laboratory where nature enforces its deepest laws with relentless precision. The key point, and the reason neutron stars exist at all, is that gravity is not the only force that matters at extreme scales. As mass increases and space shrinks, new forms of resistance appear. In white dwarf stars, it is electron degeneracy pressure that halts collapse. In neutron stars, that role is taken over by neutrons themselves. Each stage of collapse reveals a deeper layer of physics. But this balance is fragile. Neutron degeneracy pressure can only support so much mass. There is a limit, known as the Tolman-Oppenheimer-Volkoff limit, beyond which even neutrons cannot resist gravity. Its exact value depends on the unknown behavior of matter at extreme densities, but it lies somewhere around 2 to 3 times the mass of the Sun. If the collapsing core is lighter than this limit, a neutron star forms. If it is heavier, no known force can stop the collapse. Gravity continues inward without resistance, and a black hole is born. In that sense, neutron stars exist in a narrow window between survival and oblivion. This makes them deeply informative. They are objects that show us exactly where our current understanding of physics still holds, and where it might fail. The fact that neutron stars can exist at all tells us that quantum mechanics is strong enough to counteract stellar gravity, but only just. Inside the star, conditions remain extreme but stable. Temperatures cool from their initial supernova values, but densities remain crushing. The star's structure settles into layers, each governed by different physical rules. Above all of them lies the quiet truth established in this first step. Collapse does not always end in darkness. Sometimes it stops and holds. As you rest and listen now, it can feel strange to imagine such violence giving way to balance. But this is one of the universe's most consistent patterns. Forces rise, counterforces answer, and stable structures emerge not from calm beginnings, but from immense pressure resolved into order. The neutron star is not a failure to collapse. It is a success of resistance. It is matter discovering a final way to say no. And as we continue this quiet journey inward, one question remains. If collapse can be halted by quantum rules, what does matter look like once atoms themselves have disappeared? Part 2. Crushing atoms. Until they disappear. Inside a collapsing stellar core, atoms are the first to surrender. Electrons are forced into protons, combining to form neutrons in a process that releases floods of neutrinos into space. What was once an atom becomes a tightly packed sea of neutral particles. Matter loses its familiar structure, and the star becomes something closer to a single colossal atomic nucleus. To understand how profound this transformation is, it helps to remember what an atom normally is. An atom is mostly emptiness. Its nucleus is tiny, dense, and heavy, while its electrons occupy a vast surrounding cloud, held in place by electromagnetic attraction. The space between nucleus and electron is so large that if the nucleus were the size of a grain of sand, the nearest electron would orbit many meters away. All solid objects, including your own body, are built from structures that are almost entirely void. In the heart of a collapsing star, that emptiness is systematically erased. As gravity tightens its grip, atoms are pushed closer together than any ordinary force would allow. At first, electrons resist. They are governed by quantum rules that give rise to electron degeneracy pressure, the same force that supports white dwarf stars. But in a massive stellar core, gravity is stronger still. The electrons are driven inward, their available quantum states exhausted. When there is no room left for electrons to exist independently, a remarkable and irreversible process begins. Electrons are pressed directly into atomic nuclei. There, they encounter protons. Through the weak nuclear force, an electron and a proton combine to form a neutron, releasing a neutrino in the process. This is called inverse beta decay, though the name does little to capture its significance. In that moment, the atom ceases to exist. No electrons remain to define chemistry. No electromagnetic bonds survive. The periodic table, with all its complexity and variety, is erased in an instant. Hydrogen, carbon, oxygen, iron, all distinctions vanish. Matter becomes uniform, stripped down to its most neutral form. The neutrinos produced during this transformation escape almost unhindered. Trillions of them pass through the rest of the star and out into the universe, barely interacting with anything at all. For a few seconds, this neutrino outflow carries away more energy than the star emitted as light over its entire lifetime. It is a quiet evacuation of energy, invisible but immense. What remains behind is a core composed almost entirely of neutrons, packed together at densities that defy intuition. A single teaspoon of this material would weigh billions of tons. At this point, the star is no longer governed by the rules of atomic physics. It has crossed into the domain of nuclear matter. This transition is not smooth. It happens rapidly, violently, and decisively. The collapse that forces atoms to disappear unfolds in fractions of a second. Yet the consequences endure for millions or even billions of years. As the core becomes neutron-rich, its behavior changes dramatically. Neutrons do not carry electric charge, so the electromagnetic forces that once dominated matter fade into irrelevance. Instead, the strong nuclear force takes center stage. This force, which normally acts only across distances comparable to the size of a nucleus, now operates continuously throughout the star. The entire neutron star begins to resemble one vast nucleus, held together by the same force that binds protons and neutrons inside individual atoms. But unlike an ordinary nucleus, this one spans tens of kilometers and contains more mass than the Sun. Even in this extreme state, order remains. Neutrons arrange themselves according to quantum rules, filling available energy states like water, filling a deep invisible container. Their motion is constrained, their identities preserved. They are close, unimaginably close, but not merged into a single point. This is where the universe reveals an important lesson. Destruction does not always mean chaos. When atoms disappear, they do not dissolve into randomness. They reorganize into something more fundamental, something governed by deeper laws. If you could somehow observe this process from the outside, safely distant, unaffected by the gravity, you would not see atoms being crushed like fragile objects. You would see boundaries fading. You would see distinctions erased. The transition from atomic matter to neutron matter is less like breaking and more like simplifying. The star sheds complexity the way a river sheds turbulence as it slows into a lake. From the perspective of physics, this transformation is a kind of purification. Chemistry ends, molecular structure ends, only nuclear identity remains, and even that, as we will see later, may not be the final layer. At this stage, the collapsing core is still extremely hot, with temperatures reaching hundreds of billions of degrees, but heat is no longer the primary factor shaping its behavior. Density and quantum rules now dominate. The neutrons exist in a state where their individual motions are tightly constrained, their collective behavior more important than any single particle. As the collapse completes and the neutron star settles, the temperature gradually falls. Yet, the neutrons remain locked in place by degeneracy pressure. The disappearance of atoms is permanent. There is no path back to ordinary matter under these conditions. This has profound implications. It means that neutron stars preserve a record of extreme physics that cannot be recreated elsewhere. No laboratory on Earth can crush atoms so completely, so uniformly, and so sustainably. Even the most powerful particle accelerators only glimpse brief, localized echoes of these conditions. Neutron stars, by contrast, maintain them for eons. As you rest now, breathing slowly, it may feel strange to imagine matter losing its identity so completely. We are accustomed to a world where structure defines reality, where names, shapes, and boundaries matter. But the universe is under no obligation to preserve those distinctions. When pressure becomes overwhelming, nature chooses simplicity. The disappearance of atoms marks the first true step into the interior of a neutron star. Everything familiar has already been left behind. What remains is a state of matter that challenges language itself, not solid, not liquid, not gas, something denser, quieter, and more exact. And yet, even this is not the deepest transformation. Because once atoms are gone and neutrons dominate, another question slowly emerges, waiting beneath the surface. If matter can be stripped down to neutrons, what happens when even neutrons are pushed beyond their limits? Part 3. The strange pressure that holds a star. Neutron stars do not resist gravity through heat or fusion. They are held up by neutron degeneracy pressure, a quantum rule that forbids identical particles from occupying the same state. Even under crushing gravity, neutrons refuse complete overlap. This quiet quantum resistance is strong enough to support a star more massive than the Sun within a sphere barely 20 kilometers wide. To understand how unusual this is, it helps to step back and consider how pressure normally works. In everyday life, pressure comes from motion. Gas pushes outward because its molecules are constantly moving, colliding with one another and with the walls of their container. Heat increases that motion. Cool the gas enough, and the pressure fades away. But neutron degeneracy pressure does not care about temperature. It exists even at absolute zero. It arises not from motion, but from identity. Neutrons are fermions, a class of particles that obey one of the universe's most uncompromising rules. No two identical fermions may share the same quantum state. This rule, the Pauli exclusion principle, is not a force in the traditional sense. It is not something particles exert on one another. It is a restriction written into the structure of reality itself. As gravity crushes matter inward, neutrons are forced closer and closer together. At first, they can rearrange, sliding into available energy states, but space runs out quickly. The deeper the collapse goes, the fewer states remain. Eventually, there is simply nowhere left for the neutrons to go. At that point, resistance emerges, not because neutrons push back, but because the universe refuses to let them be arranged any tighter. Gravity can bend space, it can compress matter, but it cannot break this rule. The result is a pressure that increases dramatically as density rises, growing strong enough to counteract the weight of an entire star. This is why neutron stars are so small. The pressure that supports them only becomes significant when matter is compressed to extraordinary densities. The star must shrink to a city-sized sphere before neutron degeneracy pressure becomes strong enough to halt collapse. The balance that forms is delicate and precise. Gravity pulls inward relentlessly, trying to compress the star further. Degeneracy pressure rises in response, not smoothly, but steeply. A slight increase in compression produces a dramatic increase in resistance. When these two effects meet, the star settles into equilibrium. From the outside, this balance looks calm. The neutron star spins, cools, and emits radiation in steady rhythms. But inside, the tension is absolute. Every neutron is locked into place by quantum law, occupying a carefully defined state, unable to yield even the smallest amount of space. This pressure is different from anything we experience. It cannot be switched off. It does not dissipate. It does not depend on the star being active or alive. Long after fusion has ended, long after heat has radiated away, degeneracy pressure remains. In this sense, a neutron star is not a burning object. It is a frozen one, not cold in temperature, but frozen in structure. Its internal arrangement is dictated by quantum bookkeeping so strict that the star behaves like a single rigid entity. Yet this rigidity has limits. Neutron degeneracy pressure can only support so much mass. As more material is added, gravity grows stronger, squeezing neutrons into ever higher energy states. Eventually, the cost of maintaining separate states becomes too great. The pressure rises, but not fast enough. There comes a point where even this quantum resistance can no longer win. Physicists describe this limit through equations that combine general relativity and quantum mechanics. The result is a maximum mass, a boundary beyond which no stable neutron star can exist. While the exact value depends on the unknown behavior of matter at extreme densities, Observations suggest it lies around 2 times the mass of the Sun. Below this limit, neutron stars endure. Above it, collapse resumes. What makes this boundary so fascinating is what it represents. It is not just a line between 2 types of stars, it is a line between known physics and the unknown. On one side, quantum rules still hold matter apart. On the other, gravity overwhelms everything we understand. Inside a stable neutron star, degeneracy pressure does more than prevent collapse. It shapes the star's internal behavior. Neutrons fill energy levels much like electrons do in atoms, but on a vastly larger scale. Their collective arrangement determines how the star responds to stress, how it vibrates, and how it spins. When the star spins down or shifts slightly, these tightly packed neutrons can rearrange in sudden, discrete jumps. From Earth, we observe these events as glitches, tiny changes in the rotation rate of pulsars. They are whispers from deep inside the star, telling us that even in near-perfect rigidity, motion still occurs. As you lie still now, breathing gently, it can be difficult to imagine a pressure that does not come from movement or heat. We are accustomed to thinking of resistance as something active, something pushing back. But neutron degeneracy pressure is passive. It is the universe enforcing a rule. In that enforcement, something remarkable happens. A star that should collapse under its own weight simply does not. The pressure that holds it up is silent. There is no turbulence, no burning, no internal storm. Just a vast collection of particles occupying exactly the states they are allowed, and no others. This is why neutron stars are among the most stable objects known. Barring external disturbance, they can persist for millions or billions of years, slowly cooling, slowly spinning down, but never collapsing further. Their structure is locked in by principles deeper than energy balance or thermal support. And yet, even here, we are not at the end of the story. Because neutron degeneracy pressure assumes that neutrons themselves remain intact, distinct particles obeying known rules. It assumes that matter does not find a way to rearrange itself into something even more compact. Nature, however, has a habit of surprising us. As pressure increases toward the star's center, neutrons may begin to behave differently. They may pair up, flow without friction, or even dissolve into their constituent components. The very particles responsible for holding the star up may begin to change. So while neutron degeneracy pressure explains why collapse stops, it also points toward a deeper question. If this pressure is all that stands between a neutron star and total collapse, what happens in the regions where even neutrons are pushed to their limits? That is where we drift next, deeper into the star, where density becomes unfamiliar and matter begins to question its own identity. Part 4. A world where density has no meaning. At the center of a neutron star, density stops behaving intuitively. A cubic centimeter contains more mass than the Great Pyramid. Layers blur together. There is no empty space. Particles are pressed so closely that the idea of solid or liquid becomes inadequate. Matter enters phases never observed anywhere else in the universe. To appreciate what this means, it helps to pause and let go of familiar comparisons. On Earth, density is something we can picture. Wood floats, stone sinks, metal feels heavy in the hand. Even the densest materials we know still contain vast regions of emptiness between atoms. Density for us is a gentle gradient. Inside a neutron star, that gradient disappears. As you move inward from the surface toward the core, matter becomes steadily more compressed, but there's no clear boundary where one state ends and another begins. Instead, structure dissolves gradually. Atomic nuclei grow distorted, electrons vanish, neutrons crowd together until the distinction between one particle and the next becomes almost meaningless. In these depths, the concept of empty space no longer applies. In an ordinary atom, empty space dominates. In a neutron star's core, emptiness has been erased. Every available volume is occupied by matter or by the quantum states that define it. Density approaches a fundamental ceiling set by the laws of physics themselves. This is why comparisons fail. Calling the core solid implies rigidity and lattice structure. Calling it liquid suggests flow and freedom of motion. Neither description works. The matter here behaves as something entirely different, a quantum medium governed by collective rules rather than individual interactions. Physicists often describe this region using equations rather than words because language struggles to keep up. The particles are so close that their wave functions overlap. Individual identities blur into a shared quantum state. The star becomes less like an object made of parts and more like a single, coherent system. As density increases, pressure does not rise in the way we expect. In ordinary materials, compressing matter makes it stiffer, but gradually. In a neutron star, pressure skyrockets with even slight increases in density. The relationship is extreme, nonlinear, and unforgiving. This creates an environment where gravity and quantum mechanics are locked in constant tension. Gravity demands further compression. Quantum rules allow only specific arrangements. The result is a world balanced on a knife edge, where small changes in conditions can lead to entirely new states of matter. Near the core, densities may exceed several times that of an atomic nucleus. At this point, even nuclear matter, the kind found inside protons and neutrons, may no longer behave normally. The strong nuclear force, which usually binds particles into tidy clusters, becomes overwhelmed by proximity. Instead of isolated neutrons interacting occasionally, you have a continuous medium where interactions are constant and unavoidable. Forces overlap, boundaries fade, matter begins to act collectively, as if it were a single substance rather than a collection of particles. This is where many of our intuitions finally break. Temperature, for example, loses its usual meaning. In everyday terms, temperature reflects how fast particles move. But in the core of a neutron star, motion is tightly restricted. Particles occupy fixed quantum states. Their energy is dominated not by thermal motion, but by confinement and pressure. Even though the core may still be incredibly hot by human standards, temperature no longer controls behavior. Density does. If you could somehow lower a probe into this environment, ignoring for a moment the impossibility of surviving such gravity, you would not encounter anything resembling resistance in the usual sense. There would be no surface to press against, no fluid to displace. The probe would simply cease to exist, its atoms crushed instantly into the same dense medium. This is not violence in the explosive sense. It is compression so complete that distinction disappears. The idea of layers inside the star also becomes subtle here. While we speak of crusts, mantles, and cores, these are conveniences, not sharp divisions. In reality, properties change continuously with depth. Density increases smoothly. Composition shifts gradually. One phase blends into the next without ceremony. At some point, matter transitions into forms that have never existed anywhere else since the earliest moments of the universe. These are not substances you could isolate or study in a container. They exist only under the combined pressures of immense gravity and quantum constraint. This is why neutron stars are often described as cosmic laboratories. They maintain conditions far beyond anything achievable on Earth, and they do so naturally for immense spans of time. They allow the universe to explore its own laws at the edge of possibility. As you rest now, it may feel distant, abstract, even unreal. But this extreme density is not exotic for its own sake. It serves a purpose. It reveals how matter behaves when stripped of nearly everything we associate with it. In the core, matter is no longer about chemistry, structure, or form. It is about limits. How close can particles be forced together? How much mass can a given volume contain? At what point do known rules give way to new ones? These questions are not academic. The answers determine whether a neutron star remains stable or collapses further. They define the line between an object that endures and one that vanishes behind an event horizon. The uncertainty here is profound. Physicists do not yet know exactly what the deepest core contains. Different theories predict different outcomes. Some suggest exotic particles emerge. Others propose new phases of nuclear matter. Still, others hint at states that blur the distinction between matter and energy. What they all agree on is this: density, as we usually understand it, no longer applies. There is no intuitive scale left. No everyday comparison survives. Even the notion of more or less becomes abstract when space itself is saturated with mass. And yet, despite this extremity, the star remains quiet. From afar, it appears as a small, steady point of light or a rhythmic pulse of radio waves. Nothing about its appearance suggests the unimaginable compression hidden within. This contrast is one of the most humbling aspects of neutron stars. The most extreme densities in the known universe are concealed within objects that barely register on the cosmic stage. As you continue to drift deeper into this story, let that quiet contradiction settle. Enormous pressure hidden behind calm regularity. Matter pushed beyond familiarity, yet held in perfect balance. Because as density loses its meaning, another question begins to take shape. If matter can be compressed until structure disappears, what happens to motion itself inside such a world? That question waits just ahead, in the strange, silent flows beneath the star's surface. Part 5. The crust that floats on nuclear matter. Before reaching the core, you pass through a crust unlike any other. Atomic nuclei stretch into long strands and sheets, forming shapes physicists call nuclear pasta. Lasagna-like layers and spaghetti-like filaments emerge naturally under extreme pressure, minimizing energy in ways that echo biology but arise purely from physics. This region exists at the boundary between the familiar and the unimaginable. Above it, matter still resembles something we might recognize. Ions arranged in lattices, electrons moving freely between them. Below it, atoms no longer exist at all. The crust is the transition zone, the place where ordinary nuclear matter begins to lose its identity and reorganize under relentless compression. At first, the outer crust looks deceptively simple. It is made of nuclei packed into a rigid lattice, surrounded by a sea of electrons. These nuclei are heavier than anything naturally found on Earth, rich in neutrons, distorted by pressure. Gravity presses them together so tightly that even their shapes begin to change. Spheres become stretched, boundaries blur. As you drift deeper, density increases steadily. Electrons are forced to higher energies. Neutrons begin to leak out of nuclei, no longer confined to individual atomic centers. This marks the beginning of the inner crust, where matter enters a profoundly unfamiliar regime. Here, nuclear pasta begins to form. The name sounds playful, but the physics is precise. Under extreme pressure, two competing forces dominate. The strong nuclear force wants to pull protons and neutrons together. The electric force between protons wants to keep them apart. The balance between these forces, under crushing gravity, leads matter to settle into shapes that minimize energy. Spheres are no longer optimal. Instead, nuclei stretch into rods, then flatten into slabs, then twist into complex repeating structures. To human eyes, these arrangements resemble spaghetti, lasagna, gnocchi, and other pasta shapes. To physics, they are the most efficient solutions to a brutal optimization problem imposed by nature. No biology is involved, no design, no randomness. These shapes emerge because at these densities, they are the lowest energy way for matter to exist. What makes this region so remarkable is that it is neither solid nor fluid in any conventional sense. The pasta phases form ordered structures, but they are not rigid like crystal lattices. They can bend, slide, and rearrange slowly over time. Matter here behaves like a soft solid, capable of sustaining stress yet yielding under sufficient force. This has important consequences. The crust of a neutron star is responsible for many of the signals we detect from Earth. When stresses build up, from rotation slowing, magnetic fields shifting, or internal motion, the crust can crack. These starquakes release enormous energy, sometimes observed as sudden bursts of radiation or changes in the star's spin. The pasta layers sitting just above the core play a crucial role in this process. Their structure affects how stresses propagate, how energy is stored, and how suddenly it is released. In this way, the strange geometry of nuclear matter shapes events visible across the galaxy. Beneath the pasta lies something even stranger. The crust does not rest on solid ground, it floats. Below it is nuclear matter so dense that it behaves like a fluid of neutrons, possibly superfluid, flowing without friction. The crust, rigid yet fragile, sits atop this sea-like ice on dark water. The boundary between them is not sharp, but it is real. Above it, structure survives. Below it, structure dissolves. This floating crust explains another mystery: pulsar glitches. Neutron stars often rotate with extraordinary regularity, emitting pulses of radiation like cosmic clocks. Occasionally, however, their rotation suddenly speeds up slightly. These glitches are thought to occur when the crust, slowed by electromagnetic forces, suddenly shifts relative to the faster rotating interior. The pasta layers may mediate this interaction, temporarily locking and releasing angular momentum. In this way, the crust is not just a passive shell, it is an active participant in the star's behavior, coupling the deep interior to the observable surface. As you rest now, imagine this boundary: solid patterns suspended over an ocean of nuclear matter. No light penetrates here, no sound travels, yet motion exists, slow and deliberate, governed by forces older than stars themselves. The thickness of the crust is small compared to the star's radius, perhaps a kilometer or two, but its influence is outsized. It holds magnetic fields in place, it shapes emissions, it records stresses accumulated over centuries. And within it, matter performs one of the universe's quietest tricks, becoming complex under pressure, not through life or chance, but through pure necessity. The pasta phases may also influence how heat flows outward from the core. Their tangled geometry can scatter particles and impede motion, acting as an insulating layer. This affects how quickly the star cools over time, leaving subtle fingerprints in its thermal evolution. All of this happens far beyond any direct observation. We infer the crust's existence not by seeing it, but by listening to timing irregularities, to bursts of radiation, to gravitational waves from distant collisions. Each signal carries hints about how matter behaves at this strange boundary. The crust is where our familiar intuitions finally give up. It is not simply a shell. It is not simply a surface. It is a living record of extreme physics, frozen into shapes that arise once and only once in the universe. And yet, even here, we are not finished descending. Below the crust, matter loses rigidity altogether. Neutrons flow freely, pairing up and moving without resistance. Motion becomes silent, effortless, and continuous. So as we continue this quiet journey inward, another question gently emerges. If the crust floats on nuclear matter, what does that matter do when it is free to move without friction? That question carries us deeper still into the silent currents beneath the pasta, where motion exists without loss and time itself seems to slow. Part 6. Superfluid neutrons in silent motion. Deeper still, neutrons may flow without friction. In this superfluid state, matter moves endlessly without losing energy. These internal flows are thought to cause sudden changes in a neutron star's rotation, tiny glitches that ripple outward and are detectable from Earth, revealing motion hidden beneath absolute stillness. To understand how motion can exist without resistance, it helps to begin somewhere familiar. On Earth, every flow encounters friction. Water slows against riverbeds, air drags against wings. Even the smoothest motion eventually loses energy, bleeding it away as heat. Friction is so universal in daily life that we rarely question it. But friction is not a fundamental requirement of the universe. At sufficiently low temperatures and high densities, quantum mechanics allows matter to enter a phase called a superfluid. In this state, particles move together as a single coherent wave. There are no collisions in the usual sense. No energy is lost to heat. Motion, once started, can persist indefinitely. Inside a neutron star, conditions are extreme enough for this to occur naturally. As the star cools after its violent birth, temperatures drop below critical thresholds for neutron pairing. Neutrons, which are fermions, can form pairs under the right conditions, much like electrons do in superconductors. These paired neutrons behave collectively, slipping into a superfluid state that permeates much of the star's interior. This superfluid is not a liquid you could pour or splash. It is a quantum phase that fills space quietly and completely. It flows through the star's interior with perfect efficiency, responding to forces in ways that defy classical intuition. One of the most striking properties of a superfluid is how it rotates. In ordinary fluids, rotation is smooth and continuous. Stir water in a glass and it swirls in graceful curves. In a superfluid, rotation is quantized. It can only occur through the formation of tiny discrete vortices, microscopic whirlpools, each carrying a fixed amount of angular momentum. Inside a neutron star, millions or even billions of these vortices may exist, arranged in vast orderly arrays aligned with the star's rotation. They thread through the superfluid like invisible needles, defining how the entire interior spins. This arrangement is astonishingly precise. Each vortex is governed by quantum rules, yet together they determine the behavior of an object weighing more than the sun. The smallest scales of physics quietly dictate the largest. As the neutron star ages, it gradually loses rotational energy. Electromagnetic radiation carries angular momentum away, slowing the crust. But the superfluid interior does not slow as easily. With no friction, it resists change, maintaining its original rotation rate. This sets up a subtle tension between the star's outer layers and its inner depths. The crust, rigid and imperfect, is anchored to magnetic fields in external space. It slows gradually. The superfluid beneath it, however, remains stubbornly steady. The vortices that define its rotation can become pinned to irregularities in the crust, temporarily locking the two regions together. Over time, stress builds. Then, suddenly, the pinning breaks. Vortices shift. Angular momentum transfers rapidly from the superfluid to the crust. The star's rotation jumps ever so slightly, a glitch. From Earth, we observe this as a sudden change in the timing of a pulsar's radio pulses, a tiny but unmistakable signal. These glitches are one of the strongest pieces of evidence we have for superfluidity inside neutron stars. Nothing else explains how such precise, abrupt changes can occur in objects otherwise known for their extraordinary regularity. What is remarkable is not the violence of these events, but their subtlety. The changes are small, often parts per million, and yet they are detected across vast distances using instruments sensitive enough to measure timing shifts smaller than a heartbeat. In this way, silent motion deep inside a star announces itself across the galaxy. The superfluid interior also changes how we think about stillness. From the outside, a neutron star appears calm, even monotonous. Its pulses tick steadily. Its light remains constant. But beneath that appearance lies a hidden choreography of motion, flows that never slow, currents that never dissipate. This is motion without sound, without turbulence, without heat. As you rest now, breathing gently, it may feel strange to imagine movement so perfect that it leaves no trace of effort. But this is the natural consequence of quantum coherence. When particles move not as individuals but as a unified whole, resistance simply has no place to arise. The presence of superfluid neutrons also affects how the star cools. Superfluidity alters how neutrinos are emitted, how heat is transported, and how energy escapes the core. These effects subtly shape the star's thermal history, leaving signatures that astronomers can study millions of years later. Even magnetism may be influenced. Protons in certain regions of the star are thought to form superconducting phases, expelling magnetic fields into quantized flux tubes. The interaction between superconducting protons and superfluid neutrons adds another layer of complexity to the star's internal dynamics. All of this happens far below any surface we could imagine touching. No sound propagates. No light illuminates the interior. The only witnesses to this motion are the particles themselves, and, indirectly, the careful measurements made by distant observers. There is something deeply calming about this idea. Motion that does not waste energy, flow that does not erode, change that leaves structure intact. In a universe where so much is defined by loss and decay, superfluidity represents a rare exception. It is motion preserved, not diminished. And yet, even this is not the final word on the neutron star's interior. Superfluidity assumes that neutrons remain the dominant constituents, pairing and flowing according to known rules. But deeper still, pressure may rise high enough to challenge that assumption. New particles may appear. New forms of matter may emerge. So as we continue this quiet descent, another question gently presents itself. If even neutrons can flow as one, what happens when they are pushed beyond the point of remaining neutrons at all? That question waits at the edge of what we know, in the star's deepest core, where matter may finally let go of its last familiar form. Part 7. When protons and neutrons begin to blur. At greater depths, even neutrons may not remain intact. Pressure becomes so intense that the boundaries between particles soften. Protons, neutrons, and electrons begin to overlap in unfamiliar ways, challenging our understanding of what counts as a particle at all. Up to this point in our descent, the neutron has been the central character. It replaced the atom, resisted gravity through degeneracy pressure, paired into superfluids, and helped hold an entire star in balance. But the neutron is not elementary. It is itself a composite object, built from smaller components held together by the strong nuclear force. And, like every structure in nature, it has limits. As density increases toward the star's center, neutrons are pressed closer together than they ever are inside an ordinary atomic nucleus. The distance between neighboring neutrons becomes comparable to the size of the neutrons themselves. Their internal structures begin to overlap. The neat idea of one particle here and another particle there starts to lose clarity. This is where the language of particles begins to feel insufficient. In everyday physics, particles are discrete. They have positions, they have boundaries. Even in quantum mechanics, where particles behave like waves, we still speak of electrons, protons, and neutrons as identifiable entities. Inside the deep interior of a neutron star, that comfort erodes. The pressure here is not just large, it is transformative. Neutrons are made of quarks, specifically one up quark and two down quarks, bound together by gluons. Under normal conditions, these quarks are confined. They cannot escape the neutron. The force that binds them grows stronger as they are pulled apart, ensuring that quarks are never seen alone. But confinement has only been tested under conditions we can reproduce on Earth. Inside a neutron star, matter is pushed into a regime no experiment has ever reached. The question naturally arises: does confinement still hold? Physicists do not yet know the answer. Some theories suggest that at sufficient density, neutrons begin to lose their individuality. Their quarks may no longer be confined to specific particles. Instead, quarks from neighboring neutrons could mingle, forming a new state of matter where boundaries dissolve into a continuous medium. In this picture, the neutron star's core becomes something closer to a shared quark environment than a collection of particles. Matter ceases to be granular. It becomes collective in the deepest possible sense. Before reaching that extreme, however, there are intermediate possibilities. One such possibility involves the appearance of exotic particles called hyperons. These are heavier relatives of protons and neutrons, containing strange quarks in addition to up and down quarks. Under enough pressure, it may become energetically favorable for neutrons to transform into hyperons, reshaping the composition of the core. If hyperons appear, the star's internal pressure changes. Hyperons are heavier and occupy states differently, which can soften the equation of state, the relationship between pressure and density. This, in turn, affects how much mass the star can support before collapsing. The very existence of massive neutron stars observed in the universe places constraints on this process. If hyperons soften the core too much, such stars could not exist. This tension between theory and observation is one of the great unsolved puzzles of neutron star physics. Another possibility is that electrons, which largely disappeared earlier, reassert a subtle influence. At extreme densities, the distinction between electrons and other fermions can blur. Charge neutrality must be maintained, and the balance between particles becomes delicate. Small changes in composition can have large consequences. In these depths, matter is no longer described well by chemistry, nuclear physics, or even simple quantum mechanics alone. It requires a fusion of ideas, quantum chromodynamics, relativity, and many-body physics, all operating at once. From a human perspective, This is where intuition finally gives up. We are used to matter being made of things, of pieces, of building blocks stacked together. But in this environment, matter behaves more like a field than a collection. Properties emerge from interactions rather than identities. The question, "What particle is this?" becomes less meaningful than, "What state is the system in?" As you rest now, imagine definitions slowly dissolving, edges softening, categories fading. This is not destruction, it is transition. Matter is not breaking apart violently, it is reorganizing under rules deeper than the ones that govern everyday reality. And all of this happens quietly. There are no explosions inside the star's core, no flashes of light, no sound. The transformations unfold steadily, enforced by pressure and equilibrium. The star adjusts itself to whatever configuration minimizes energy under these impossible conditions. What makes this region so fascinating is not just what might be there, but what it tells us about the limits of knowledge. We cannot reproduce these conditions. We cannot send probes. We infer, constrain, and imagine, guided by equations and distant observations. Gravitational waves from neutron star mergers offer brief glimpses into this regime. The way stars deform, oscillate, and collapse during collision depends sensitively on what their cores are made of. Each detection narrows the range of possibilities, slowly illuminating the darkness. But even with these clues, much remains uncertain. Do neutrons dissolve smoothly into quark matter, or does the transition happen abruptly, like water freezing into ice? Are there multiple layers of exotic matter stacked within the core, or a single dominant phase? Does matter there behave like a fluid, a solid, or something that fits neither word? The universe has not yet answered these questions clearly. What we do know is that the deeper you go, the less useful familiar labels become. Protons and neutrons blur not because they are destroyed, but because the environment no longer allows them to remain distinct. This blurring has philosophical weight as well as scientific importance. It reminds us that the categories we rely on are context-dependent. They work beautifully within certain ranges of scale and energy. Outside those ranges, they must be revised or abandoned. Inside a neutron, star matter teaches us humility. It shows us that even the most basic concepts, particle, boundary, identity, are not absolute. They are conveniences, effective descriptions that hold only as long as conditions permit. And yet, even here, nature remains lawful. The blurring is not chaos. It follows rules, even if we have not fully deciphered them. The star does not collapse into randomness. It settles into whatever configuration the laws of physics demand. As we continue this slow descent, definitions will soften further still. Because if protons and neutrons can lose their individuality, another question quietly emerges. What happens when matter gives up particles altogether and becomes something even more fundamental? That question carries us onward toward the possibility that at the very center of the star, quarks themselves may roam free, no longer bound into anything we would recognize as matter at all. Part 8. Could quarks roam free at the core? Some theories suggest that at the very center, neutrons dissolve into their constituent quarks. Instead of individual particles, the core may become a quark soup, a dense interacting fluid of fundamental components no longer confined inside neutrons. If true, neutron stars may hide a state of matter last seen just after the Big Bang. To understand how radical this idea is, it helps to recall what quarks normally are. Quarks are never seen alone. They are permanently confined inside larger particles like protons and neutrons, bound together by the strong nuclear force. This force grows stronger as quarks are pulled apart, ensuring that isolation is impossible under ordinary conditions. For decades, confinement has been one of the most reliable principles in particle physics. But confinement, like all physical laws, exists within a context. Inside the core of a neutron star, pressure and density rise to extremes far beyond anything achievable in laboratories. Neutrons are pressed together so tightly that their internal quark structures may overlap. The distinction between one neutron and the next begins to dissolve, and with it, the idea that quarks must belong to a single particle. In this environment, confinement may weaken, not because the strong force disappears, but because the conditions change the balance of energy. It may become energetically favorable for quarks to exist in a shared state rather than remain locked inside individual neutrons. If this happens, the core transitions into quark matter. Quark matter is not empty or chaotic. It is dense, strongly interacting, and highly ordered in its own way. Quarks still feel the strong force, but now they interact across a continuous medium rather than within isolated particles. Instead of neutrons bumping against one another, you have quarks flowing through a shared environment governed by collective rules. This state is sometimes described as a quark-gluon plasma, though the term can be misleading. In particle accelerators, quark-gluon plasma exists at extremely high temperatures for fleeting moments. In neutron stars, the same components may exist at relatively low temperatures but crushing densities. The physics is similar in spirit, but different in detail. What makes this possibility so compelling is its connection to the early universe. Just microseconds after the Big Bang, the universe was so hot and dense that quarks could not form protons or neutrons. Everything existed in a primordial soup of quarks and gluons. As the universe expanded and cooled, quarks became confined, giving rise to the matter we know today. If neutron stars contain quark matter, they are preserving that ancient state, not through heat but through pressure. They would be cosmic time capsules, holding within them conditions that existed only briefly at the dawn of time. This idea reshapes how we think about neutron stars. They would not be uniform objects made solely of neutrons, but layered systems with radically different phases of matter stacked one inside another. Ordinary nuclear matter outside, exotic phases deeper in, and perhaps at the very center, a quark core. But how would such a core behave? Quark matter may be more compressible than neutron matter, or it may be stiffer, depending on how quarks interact at these densities. Some models suggest that quark matter could actually help support the star, allowing it to remain stable at higher masses. Others suggest the opposite, that its presence would make collapse more likely. Observations are beginning to constrain these ideas. Astronomers have measured neutron stars with masses around 2 times that of the Sun. Any viable theory of quark matter must allow such massive stars to exist. This rules out many models and keeps the question open. Another intriguing possibility is that quark matter might form not as a simple fluid, but as an organized phase. Quarks could pair up in patterns, forming a color superconductor, a state where certain combinations of quarks move coherently, reducing energy and increasing stability. In this picture, the core would not be turbulent or disordered. It would be calm, rigid in a quantum sense, and deeply structured. Motion would still occur, but under rules even more abstract than those governing superfluid neutrons. As you rest now, imagine matter shedding one layer of identity after another. First, atoms disappear. Then, neutrons blur. Now, even the particles that once defined neutrons may no longer stand alone. What remains is not emptiness, but something simpler and deeper. The challenge in confirming quark matter lies in its invisibility. We cannot observe the core directly. We must infer its presence through indirect effects: the star's mass, its radius, how it deforms under tidal forces, and how it vibrates when disturbed. Gravitational waves from neutron star mergers are especially promising. The way stars stretch and compress as they spiral together depends on the stiffness of their interiors. Subtle differences in the waveform carry information about whether the core contains ordinary nuclear matter or something more exotic. In some simulations, stars with quark cores behave differently during merger, collapsing more readily or producing distinctive signals. As detectors improve, these differences may become measurable. There is also the possibility that quark matter could trigger sudden transitions within a star. If conditions change, for example, as the star spins down and pressure increases, the core might convert from neutron matter to quark matter abruptly. Such a transition could release energy, potentially observable as a burst of radiation or a sudden change in rotation. These ideas remain speculative, but they are grounded in known physics extended into unfamiliar regimes. What is certain is that the question of quark matter sits at the frontier of our understanding. It connects the smallest scales of particle physics with the largest scales of astrophysics. It asks whether the rules that govern subatomic particles can reshape entire stars, and it does so quietly. There is no dramatic announcement when matter crosses this boundary, no visible marker. The transformation, if it occurs, is internal and hidden, proceeding according to equilibrium and necessity. This quietness is a recurring theme inside neutron stars. The most extreme conditions in the universe do not announce themselves with noise or light. They exist in balance, hidden behind steady pulses and faint emissions. As we drift further inward, another subtle question arises. If quarks can roam free, could they arrange themselves into forms even stranger still? Could there exist states of matter more stable than anything we have imagined? States that redefine what it means for matter to exist at all? That question leads us onward toward the possibility of strange matter and the idea that some neutron stars may be something even more exotic than their name suggests. Part 9. The possibility of strange matter. Under enough pressure, strange quarks may appear, creating particles called hyperons or even strange matter. This exotic form could be more stable than ordinary nuclear matter, raising a profound possibility that neutron stars might transform entirely into strange stars, objects even denser and more alien. To understand why this idea matters, it helps to recall how matter usually behaves. In ordinary conditions, protons and neutrons are built only from up and down quarks. Strange quarks are heavier and short-lived, appearing briefly in high-energy collisions before decaying away. In the calm, low-pressure universe we inhabit, strange quarks have no reason to linger. But the interior of a neutron star is not calm. As pressure rises toward the center, the energy cost of maintaining matter in its familiar forms increases. Neutrons are squeezed into ever tighter arrangements. Their internal quarks are forced into higher energy states. Eventually, it may become energetically favorable for some of those quarks to change identity. This is where strangeness enters the story. A strange quark is heavier than an up or down quark, but it can lower the overall energy of the system by allowing matter to distribute itself more evenly across available quantum states. Under sufficient pressure, creating strange quarks may actually reduce the total energy, even though each individual quark is heavier. Nature always chooses the lowest energy configuration available. If conditions allow, neutrons may transform into particles containing strange quarks. These particles are known as hyperons, cousins of the proton and neutron, but heavier and more exotic. Their appearance would fundamentally change the makeup of the star's core. Instead of being composed almost entirely of neutrons, the core would become a mixture of particles, each carrying different quark content. This diversity would alter how pressure builds with density, changing the star's internal balance. This possibility is both enticing and troubling. On the one hand, hyperons are a natural extension of known physics. We observe them in particle accelerators. We understand their properties. On the other hand, introducing hyperons into neutron star models often creates a problem. Hyperons tend to soften the equation of state, meaning that pressure increases more slowly with density. If pressure rises too slowly, the star cannot support as much mass. Yet we observe neutron stars with masses around 2 times that of the Sun. This means that if hyperons do appear, their effects must be carefully balanced. Either their interactions are different under extreme conditions, or something else provides additional support. This tension is known as the hyperon puzzle, and it remains unresolved. Beyond hyperons lies an even more radical idea. If strange quarks become abundant enough, matter may transition into a state called strange matter, a form of quark matter composed roughly equally of up-down and strange quarks. Some theories suggest that strange matter could be more stable than ordinary nuclear matter, not just under pressure, but in general. If this is true, the implications are extraordinary. It would mean that the true ground state of matter is not iron or nuclei or neutrons, but strange quark matter. Ordinary matter would be metastable, stable only because the conditions required to convert it are rarely met. In this view, neutron stars could act as cosmic furnaces where matter crosses this threshold. Once a seed of strange matter forms, it could grow, converting surrounding nuclear matter into more strange matter. Over time, the entire star could transform into a strange star. Such a star would look similar to a neutron star from the outside, but its interior would be fundamentally different. Instead of layers of nuclei, neutrons, and exotic phases, it would be composed almost entirely of strange matter, possibly all the way to the surface. The surface itself would be unusual. Strange matter might be self-bound, held together by the strong force rather than gravity alone. This could allow strange stars to have sharper edges and different emission properties than neutron stars. Detecting such differences is challenging, but not impossible. Astronomers search for subtle clues, unusual mass-radius relationships, unexpected cooling behavior, or peculiar bursts of radiation. So far, no definitive strange star has been identified, but the possibility remains open. As you rest now, imagine matter quietly choosing a new identity, not through violence or decay, but through preference. Under enough pressure, the universe may decide that strangeness is simpler, that adding a new type of quark lowers the cost of existence. This is not an intuitive idea. We tend to think of heavier components as less stable. But in dense systems, balance matters more than simplicity. Adding strange quarks can relieve pressure, spread energy more evenly, and create a deeper minimum in the energy landscape. In this way, strange matter is not exotic for the sake of being exotic. It is exotic because the environment demands it. The existence of strange stars would blur the boundary between astrophysics and particle physics even further. Entire stars would become laboratories for the strong force, testing how quarks behave when freed from their usual constraints. It would also force us to rethink the life cycle of compact objects. A neutron star might not be the final stage before black hole formation. It could be an intermediate phase, capable of transforming into something else entirely. Even the idea of identity becomes slippery here. At what point does a neutron star stop being a neutron star? Is it defined by its history, its appearance, or its internal composition? These questions are not merely semantic. They reflect how deeply our categories depend on context. Strange matter also raises quieter, more philosophical considerations. If strange matter is truly more stable than ordinary matter, why does the universe not convert everything into it? The answer lies in barriers. Conversion requires extreme pressure or energy. Without those conditions, matter remains trapped in its familiar state. The universe, it seems, is full of such barriers, thresholds that keep things as they are until conditions become overwhelming. Inside neutron stars, those thresholds are crossed. And yet, even here, nothing is rushed. Transformations proceed according to equilibrium. Matter explores possibilities slowly, constrained by conservation laws and quantum rules. There is a calm inevitability to it. Whether strange matter exists inside neutron stars remains an open question. Future observations may confirm it, or they may rule it out. Either outcome will teach us something profound about how matter behaves at its limits. What is already clear is that neutron stars are not simple objects. They are not just balls of neutrons. They are layered, dynamic systems where matter continuously negotiates with pressure, identity, and stability. As we continue our descent, one more aspect of this extreme environment waits to be explored. Because, regardless of what matter becomes, neutrons, quarks, or something stranger still, gravity never loosens its grip. And where gravity is strongest, it does more than compress matter. It bends time itself. That quiet distortion is the next truth waiting beneath the surface. Part 10. Gravity so strong. It bends time itself. Near the core, gravity slows time measurably. A clock buried deep inside a neutron star would tick more slowly than one on its surface. Space and time curve so steeply that the star becomes a laboratory for general relativity, testing Einstein's equations at their breaking point. To understand why time itself begins to behave strangely here, we have to let go of the idea that time flows at the same rate everywhere. In everyday life, seconds feel universal. A heartbeat lasts roughly the same no matter where you are. A minute passes with quiet consistency. But this sense of uniform time is an illusion born of weak gravity. Einstein showed us that gravity is not just a force pulling objects together, it is a curvature of space-time itself. Mass tells space how to bend, and that bending tells matter and light how to move. Time is woven into this fabric. When space curves, time stretches. On Earth, this effect is tiny. A clock on the ground ticks ever so slightly slower than one on a satellite orbiting above, farther from the planet's gravity. The difference is real, measurable, and routinely corrected for in GPS systems. But it is so small that we never feel it. Near a neutron star, the effect is no longer subtle. The star's mass is compressed into an extraordinarily small volume, creating a gravitational field second only to that of a black hole. As you approach the star, space-time curves more sharply. Time slows, not metaphorically, not poetically, but physically. If you could hover near the surface of a neutron star, ignoring for a moment the impossibility of surviving such gravity, you would find that your clock runs noticeably slower than one far away. Signals you send outward would appear redshifted, stretched to longer wavelengths as they climb out of the gravitational well. Deeper still, the effect intensifies. Near the core, the passage of time slows dramatically compared to the outside universe. A second inside the star does not correspond to a second elsewhere. The star becomes temporally layered, with different regions experiencing time at different rates. This is not science fiction. It is a direct consequence of general relativity. What makes neutron stars so valuable to physicists is that they sit at the edge of relativistic extremes without crossing into total collapse. Black holes hide their interiors behind event horizons, cutting us off from direct information. Neutron stars, by contrast, expose their gravity without sealing it away. They allow us to study strong field gravity in the open. Every pulse emitted by a neutron star carries the imprint of this curvature. The star's rapid rotation, sometimes hundreds of times per second, interacts with its intense gravity to produce effects like frame dragging, where space-time itself is pulled along by the star's spin. In this region, space does not sit still. It twists. Frame dragging causes the paths of particles and light to curve in unexpected ways. Orbits precess, magnetic fields warp. The star's rotation becomes inseparable from the structure of space-time around it. As you rest now, breathing slowly, imagine time itself becoming thicker, heavier, less willing to move, not frozen but stretched, like honey flowing more slowly under its own weight. This stretching of time affects everything inside the star. Nuclear reactions, particle interactions, even the decay of unstable particles all proceed at rates determined by local time. From the outside, these processes appear slowed. In a sense, the neutron star is aging more slowly than the rest of the universe. This raises a subtle but profound point. When we speak of the age of a neutron star, whose time are we using? The time measured far away, or the time experienced deep within its core? In relativity, both are valid, but they are not the same. There is no single universal clock. This temporal distortion also affects how we interpret observations. The frequencies we detect from pulsars are shifted by gravitational redshift. The light we see has lost energy climbing out of the star's gravity. By measuring these shifts, astronomers can infer how compact the star is, how strong its gravity must be. In this way, time bending becomes a diagnostic tool. But neutron stars push relativity further still. Their interiors may host densities where the equations of general relativity and quantum mechanics must both be applied simultaneously. This is a regime we do not fully understand. Our best theories were never designed to coexist so closely. Einstein's equations work beautifully for gravity. Quantum mechanics works beautifully for particles. Inside a neutron star, both are essential and neither is sufficient alone. This makes the core a proving ground for new physics. Does space-time behave smoothly all the way down, or does it develop new structure at extreme densities? Does time slow continuously, or are there thresholds where behavior changes abruptly? These questions remain open. What we do know is that gravity inside a neutron star is strong enough to noticeably alter the flow of time without sealing it off completely. The star exists in a delicate middle ground where relativity is extreme but not absolute. This balance is rare in the universe. As you drift deeper into this thought, it becomes clear that gravity is not merely shaping matter here. It is shaping experience itself. If there were a conscious observer inside the star, a purely hypothetical notion, their perception of time would be profoundly different from ours. Moments would stretch. External events would appear to race ahead. The universe outside would seem accelerated, while the interior remained calm and deliberate. This is not because anything inside is moving slowly, but because time itself is. And yet, despite this distortion, the star remains stable. Its gravity does not tear it apart. Its time does not stop. Everything continues, governed by laws that remain consistent even under such strain. This consistency is one of the quiet triumphs of physics. The same equations that describe falling apples and orbiting planets also describe the behavior of time near the densest stars in the universe. Neutron stars remind us that relativity is not an abstract theory reserved for black holes in cosmology. It is active, present, shaping objects we can observe and measure. As you lie still now, it may feel grounding to remember that time itself is not fixed. It responds to mass, to motion, to depth in a gravitational field. Your own clock, right now, is ticking at a rate determined by your position in the universe. Inside a neutron star, the ticking slows, quietly and precisely. And this leads naturally to another question. If gravity can bend time so strongly without breaking space-time, how close is a neutron star to the ultimate limit? How near does it stand to the point where time slows beyond recovery and collapse becomes inevitable? That question draws us toward the edge, the boundary between neutron stars and black holes, where gravity's grip tightens to its final extreme. Part 11. Magnetism. Born from compression. As the star collapses, magnetic fields are squeezed and amplified to unimaginable strengths. Some neutron stars become magnetars, their magnetic fields trillions of times stronger than Earth's. These fields reach deep into the core, shaping particle behavior and occasionally cracking the star's crust with silent, catastrophic force. To understand how such magnetism is born, it helps to remember a simple rule of physics. Magnetic fields are conserved when matter collapses. This is known as magnetic flux conservation. When a region of space threaded by magnetic field lines shrinks, those lines are forced closer together. The field grows stronger, not because anything new is created, but because what already existed is compressed. Before collapse, a massive star already carries a magnetic field. It may be modest by cosmic standards, comparable to that of the Sun. But when the star's core contracts from a sphere millions of kilometers wide into one only tens of kilometers across, that same magnetic flux is squeezed into a vastly smaller volume. The result is amplification on an almost incomprehensible scale. A field that was once gentle becomes intense. A field that once guided charged particles now dominates them. In some neutron stars, this process produces magnetic fields of around 10 to the power of 12 Gauss, already a trillion times stronger than Earth's field. In magnetars, the most extreme cases, the field strength climbs even higher, reaching 10 to the power of 14 or 15 Gauss. At these levels, magnetism is no longer just a background influence. It becomes one of the defining forces shaping the star's behavior. To appreciate how strong this is, consider what such a field would do elsewhere. A magnetar's field could erase the magnetic stripe on a credit card from halfway to the moon. It would distort the electron clouds of atoms, changing their shapes and energy levels. It would pull apart molecules and alter the vacuum itself. Near a magnetar, empty space does not behave as emptiness anymore. Quantum electrodynamics predicts that at extreme field strengths, the vacuum becomes polarized. Virtual particles flicker into alignment. Light propagates differently depending on its polarization. Space itself becomes a medium influenced by magnetism. Inside the neutron star, these fields thread through matter already pushed to its limits. Charged particles, protons, electrons, and quarks, are forced to move along magnetic field lines. Their motion perpendicular to the field is tightly constrained, quantized into discrete orbits. The field becomes a kind of invisible scaffold, guiding how matter arranges itself. This has consequences deep within the star. Magnetic fields interact with superfluid and superconducting phases in the interior. Protons, thought to form a superconducting fluid in some regions, expel magnetic fields into thin quantized flux tubes. These tubes thread through the star, interacting with neutron vortices and crustal structures. The result is a complex internal dance between magnetism, rotation, and quantum order. As the star spins and slows, these internal structures shift. Magnetic stress builds in the crust, which is rigid but not infinitely strong. The crust resists deformation, storing energy like a compressed spring. Eventually, it yields. When the stress exceeds what the crust can bear, it cracks. These events are known as starquakes. Unlike earthquakes on Earth, they do not produce sound waves in air or ground. They release energy primarily through electromagnetic radiation and particle acceleration. From across the galaxy, we detect these moments as sudden flashes of X-rays or gamma rays, brief, intense bursts that outshine entire stars for fractions of a second. In magnetars, these outbursts can be especially powerful. The strongest observed giant flares release more energy in a tenth of a second than the sun emits in thousands of years. And yet, the star itself remains intact, settling back into equilibrium after the release. There is something quietly unsettling about this. Enormous energy stored, enormous energy released, and then calm again. No explosion, no destruction, just adjustment. As you rest now. Imagine pressure building invisibly, patiently, beneath a surface that looks unchanged. Then, a sudden release, not loud, not violent in the human sense, but absolute in its force. This is how magnetars speak. Magnetism also affects how neutron stars cool and age. Strong fields channel heat along certain directions, creating hot spots on the surface. These spots rotate in and out of view, producing pulses of radiation that help us map the star's magnetic geometry. In this way, magnetism becomes visible, but its deepest influence may be hidden. Some theories suggest that magnetic fields can affect which phases of matter are stable inside the star. They may favor certain arrangements of particles, suppress others, or alter the thresholds at which transitions occur. In extreme cases, magnetism could even influence whether quark matter or strange matter forms, subtly reshaping the star's deepest core. What makes this so fascinating is that magnetism, a force we encounter casually in daily life, becomes something entirely different under compression. A refrigerator magnet is playful, a compass needle is gentle. Inside a neutron star, magnetism is structural. It shapes reality. And yet, it is still governed by the same equations. This continuity is one of the quiet comforts of physics. The laws that describe magnets on Earth scale upward without contradiction, revealing new behavior, but never abandoning consistency. Magnetars, despite their ferocity, are not anomalies. They are natural outcomes of collapse under the right conditions. A slight difference in rotation, composition, or initial field strength can tip a neutron star into this extreme magnetic state. Once there, the star carries that magnetism for thousands or millions of years, slowly decaying as energy leaks away. As time passes, the field relaxes, stresses diminish, outbursts become less frequent. The star settles into a quieter existence, still magnetized but less volatile. Even in their most active phases, magnetars remind us of a recurring theme in this journey. The universe's most extreme phenomena often unfold in silence, punctuated by brief signals that travel vast distances to reach us. Inside the star, there is no sound, no flash, just forces balancing, adjusting, finding new equilibrium. As we continue deeper into the structure of neutron stars, magnetism teaches us an important lesson. Compression does not merely shrink matter, it amplifies its hidden properties, revealing aspects of reality that remain subtle elsewhere. Gravity compresses, density rises, time slows, matter transforms, and magnetism, once a background feature, becomes a dominant architect. This brings us to a quiet but critical question. If magnetism, pressure, and gravity all push matter toward ever more extreme states, how close can a neutron star come to collapse before it crosses a final boundary? That question leads us to the edge, the delicate line between endurance and disappearance, where the star must either hold itself together or surrender to gravity completely. Part 12. The edge of collapse. There is a limit to how much mass neutron matter can support. Beyond it, even degeneracy pressure fails. The core teeters on the edge between stability and total collapse. This boundary, still uncertain, defines the maximum mass of a neutron star and the threshold of black hole formation. Up to this point, every layer of the neutron star has told the same quiet story. Gravity presses inward, matter responds with deeper and stranger forms of resistance, atoms give way to neutrons, neutrons organize into superfluids, exotic particles may appear, quarks may roam, magnetic fields tighten, time slows. Again and again, the universe finds a way to hold itself together. But this process does not continue forever. Gravity is patient and it does not weaken with time. As mass increases, its pull deepens, demanding ever more resistance. Degeneracy pressure, no matter how strange or powerful, is not infinite. It has a ceiling. And when that ceiling is reached, balance becomes impossible. This is the edge of collapse. Physicists describe this boundary using a concept known as the maximum neutron star mass. Below it, equilibrium is possible. Above it, no known state of matter can provide enough pressure to counter gravity. The star must continue collapsing, and the outcome is inevitable. A black hole forms. The precise location of this boundary is one of the great open questions in astrophysics. It depends on the behavior of matter at densities we cannot reproduce or fully calculate. It depends on whether exotic particles appear, whether quark matter exists, whether strange matter stabilizes or destabilizes the core. Different assumptions lead to different limits. What we do know comes from observation. Astronomers have measured neutron stars with masses around 2 times that of the Sun. These stars exist. Therefore, whatever physics governs their interiors must allow such masses to be supported. Beyond that, the picture grows uncertain. Some models allow neutron stars up to about 2.3 solar masses. Others stretch closer to 2.5. Very few allow much more. Somewhere in this narrow range lies the true boundary, the moment when gravity finally overwhelms all forms of matter. This uncertainty is not a weakness of science. It is a sign that we are approaching the edge of what is knowable with current tools. Inside a neutron star approaching this limit, conditions are extreme even by neutron star standards. Central densities soar, pressure gradients steepen, time dilation grows stronger. The star becomes more compact, more relativistic, more tightly bound. Small changes matter here. Adding even a fraction of a solar mass can tip the balance. A neutron star accreting matter from a companion may cross the threshold slowly, quietly, without any outward sign until the final moment. There is no warning flare, no gradual tearing apart. One moment, the star exists. The next, it does not. The collapse to a black hole, once triggered, happens rapidly. In milliseconds, the core shrinks beyond its own Schwarzschild radius. An event horizon forms. Information about the interior becomes permanently hidden from the outside universe. From the perspective of an external observer, time appears to slow near this boundary. Signals from the collapsing star stretch and fade. The final moments blur into darkness. The star seems to freeze at the edge, never quite completing its fall. From the star's own perspective, the collapse is swift and final. This duality is one of the most unsettling aspects of relativity. Different observers disagree about the sequence of events, yet all are correct within their own frames of reference. As you rest now, it may feel strange to imagine an object so stable, so enduring, simply ceasing to exist as a star. But collapse is not destruction in the explosive sense. It is a change of state, a reconfiguration of space-time itself. The neutron star does not blow apart. It does not fragment. It becomes something else entirely. What makes this edge so compelling is how narrow it is. Neutron stars live close to it by definition. They are objects that have already exhausted most forms of resistance. They exist only because quantum rules intervene at the last moment. They are survivors, but barely. This precariousness is reflected in their behavior. Small perturbations, accretion, spin-down, magnetic evolution can have outsized consequences. A star that has remained stable for millions of years may cross the boundary with little external drama. In binary systems, this process can be observed indirectly. As a neutron star pulls matter from a companion, its mass increases. Astronomers watch closely, knowing that somewhere ahead lies a point of no return. The edge of collapse also appears in neutron star mergers. When two neutron stars collide, their combined mass often exceeds the maximum stable limit. For a brief moment, a hypermassive neutron star may form, supported by rapid rotation and thermal pressure. But this support is temporary. As rotation slows and heat radiates away, the star loses what little extra resistance it had. Gravity wins. The object collapses into a black hole, often within seconds. Gravitational waves from these events carry the signature of this transition. The waveform changes abruptly when the collapse occurs, marking the moment when matter can no longer hold space-time open. In this way, the edge of collapse is not just theoretical. It is written into signals we can detect across the universe. There is something profoundly humbling about this boundary. It reminds us that no structure, no matter how exotic or well-supported, is immune to gravity's ultimate demand. Resistance can delay collapse, reshape it, and complicate it, but it cannot always prevent it. And yet, the fact that neutron stars exist at all is extraordinary. They represent the ideal last stand of matter against gravity, the final configuration where particles, pressure, and quantum rules still matter. Beyond this point, the concept of matter itself loses meaning, replaced by geometry and horizons. As we move through this story, it becomes clear that neutron stars are not merely objects, they are thresholds. They mark the transition between a universe where matter defines structure and one where space-time alone takes control. This makes them invaluable. By studying where neutron stars end and black holes begin, we learn not only about stars but about the fundamental limits of physical law. Where does quantum resistance fail? Where does gravity become absolute? Where does time stop behaving like time? These are not abstract questions. They are encoded in the mass, radius, and behavior of real objects scattered across the galaxy. As you continue to drift through this quiet exploration, let this boundary settle gently in your thoughts. Stability balanced against inevitability. Endurance pressed up against surrender. Because at the edge of collapse, the universe reveals one of its deepest truths. Everything holds until it doesn't. And in the final moments before that boundary is crossed, the neutron star tells us everything it can about how matter resists, adapts, and finally yields. From here, our journey turns outward again, toward how we learn these truths at a distance, how signals, waves, and light carry whispers of these hidden interiors across the vast calm of space. Part 13. What we can learn without going there. We cannot probe neutron star cores directly. Instead, scientists listen. Tiny changes in rotation, gravitational waves from collisions, and subtle shifts in light reveal clues about the matter inside. Each observation narrows the possibilities, turning distant stars into experiments written across space-time. From a human perspective, this might feel like a limitation. We are used to learning by touching, by opening, by dissecting. We send probes to planets, land rovers on distant worlds, drill into ice and rock. But neutron stars sit far beyond any such reach. Their gravity would tear apart any spacecraft long before it came close. Their interiors are sealed behind pressures no instrument could survive. And yet, they speak. They speak through timing so precise it rivals atomic clocks. They speak through ripples in space-time that pass silently through Earth. They speak through light stretched and shifted by gravity. In these signals, scientists find a remarkable truth. Even without direct access, nature leaves fingerprints everywhere. One of the most powerful tools in this quiet investigation is rotation. Many neutron stars are pulsars, emitting beams of radiation that sweep past Earth like lighthouse beams as the star spins. These pulses arrive with astonishing regularity. Some pulsars rotate hundreds of times per second, their timing stable to better than a microsecond over years. This precision turns pulsars into cosmic clocks. When those clocks falter, even slightly, something inside the star has changed. A glitch, a sudden increase in rotation rate, suggests a transfer of angular momentum between the superfluid interior and the crust. The size, frequency, and recovery of these glitches carry information about how matter behaves under extreme density. By studying these tiny irregularities, scientists infer the presence of superfluids, vortex pinning, and crustal rigidity, all without ever seeing the interior itself. Light, too, carries clues. As radiation escapes from the surface of a neutron star, it climbs out of a deep gravitational well. In doing so, it loses energy. Its wavelength stretches. This gravitational redshift depends on how compact the star is, on the ratio between its mass and its radius. By measuring the spectra of X-rays emitted from the surface, astronomers can estimate how strongly gravity is bending space-time. These measurements help constrain how dense the star must be, which in turn restricts which equations of state, which models of dense matter, are possible. Sometimes the surface itself becomes visible in unexpected ways. Thermal emission reveals how heat flows from the interior to the outside. Hotspots appear where magnetic fields channel energy outward. As the star rotates, these regions brighten and dim, allowing scientists to map surface geometry and infer internal processes. Cooling curves, showing how neutron stars lose heat over time, provide another window inward. Different internal compositions allow energy to escape at different rates. Some forms of matter emit neutrinos more efficiently than others. By comparing observed temperatures with theoretical models, researchers narrow down what the core might contain. And then there are gravitational waves. When two neutron stars spiral toward each other and collide, they shake space-time itself. Detectors on Earth register these ripples as faint, passing distortions lasting only seconds. Yet within those seconds lies a wealth of information. The way neutron stars deform as they orbit depends on how stiff or soft their interiors are. This deformability leaves an imprint on the gravitational wave signal. By analyzing the waveform, scientists can infer how easily each star was stretched by its companion's gravity. Stiffer stars resist deformation, softer stars yield more readily. Each possibility corresponds to different internal physics. The aftermath of the collision speaks as well. Whether the merged object briefly survives as a massive neutron star or collapses immediately into a black hole depends on the maximum mass neutron matter can support. The timing of collapse, if it occurs, places direct limits on the edge of stability we explored earlier. In these violent mergers, neutron star interiors briefly reveal themselves, not through direct observation, but through motion and response. There is a quiet elegance to this approach. Rather than forcing entry, scientists observe how the system behaves under stress. They watch how it bends, how it rings, how it settles. From that behavior, they infer structure. This method is not new. It mirrors how seismologists study Earth's interior using earthquakes, or how doctors infer the structure of organs through imaging and vibration. Neutron stars are simply the most extreme application of this principle. Even neutrinos play a role. During the birth of a neutron star in a supernova, vast numbers of neutrinos escape from the collapsing core. In rare cases, such as supernova 1987A, detectors on Earth have captured these particles. Their energies and arrival times provide information about the conditions deep inside the forming neutron star. Though brief, these neutrino signals confirm key aspects of collapse models, offering rare glimpses into the earliest moments of neutron star existence. As you rest now, it may feel reassuring to know that understanding does not always require closeness. Sometimes, distance sharpens perception. The universe, vast as it is, carries its stories outward, encoded in motion and light. Neutron stars challenge us to listen carefully. They remind us that science is not about conquering nature, but about paying attention, about noticing patterns, about letting reality reveal itself in the ways it chooses. Every observation narrows the field of possibilities. Models that predict stars too small, too soft, or too fragile are ruled out. Those that survive must accommodate all known signals, mass measurements, timing behavior, cooling rates, merger outcomes. This process is slow, deliberate, and deeply patient. There is no single experiment that will solve the mystery of neutron star interiors. Understanding emerges gradually, through accumulation and refinement. Each new detection adjusts the picture slightly, bringing it into sharper focus. And yet, uncertainty remains. This is not a failure, it is an invitation. The unknown interior of neutron stars sits at the intersection of disciplines. It draws together astrophysics, nuclear physics, particle physics, and relativity. Progress in one area informs the others. Observations guide theory. Theory guides observation. In this way, neutron stars become bridges, not just between states of matter, but between fields of knowledge. As you lie still now, consider the quiet power of inference. Without touching, without seeing, without entering, we learn. We listen to the universe speaking softly across unimaginable distances. And in those whispers, we find answers, incomplete, provisional, but real. As our journey continues, one final perspective begins to take shape. Because sometimes, the most revealing moments come not from steady observation, but from rare, dramatic events. Collisions so powerful they briefly expose everything we've been listening for all along. That is where we drift next, toward the moments when neutron stars meet. The universe rings with their encounter. Part 14. Collisions that shake the universe. When two neutron stars merge, their cores briefly expose extreme states of matter before collapsing. The resulting gravitational waves carry information about stiffness, density, and composition, echoes of conditions unreachable by any laboratory on Earth. For most of their lives, neutron stars exist in quiet isolation, spinning steadily, cooling slowly, locked into rhythms that can last millions or billions of years. But some are born in pairs. Two massive stars orbit one another, live together, and die together. When both collapse into neutron stars, their partnership continues, now governed by gravity so intense that separation becomes temporary. Over time, their orbit shrinks. Gravitational waves carry energy away, rippling outward through space-time. The stars spiral closer, slowly at first, then faster, then with mounting inevitability. Each orbit shortens, each pass grows tighter. What unfolds is not sudden chaos, but a long, graceful inward dance, silent and precise. As they draw near, something remarkable happens. The immense gravity of each star begins to deform the other. They stretch slightly, losing their perfect spherical shapes. This deformation depends on what the stars are made of. Stiffer interiors resist distortion, softer ones yield more easily. The difference is subtle, but it is written clearly into the gravitational waves they emit. These waves travel unhindered across the universe. When they pass through Earth, they compress and stretch space by less than the width of a proton. Instruments like LIGO and Virgo detect these changes not by force, but by patience, by watching light interfere with itself across long distances. In these tiny signals, the universe encodes the behavior of matter under conditions no experiment can reproduce. As the neutron stars approach their final moments, their internal structures are pushed to the limit. Tidal forces churn their interiors, superfluid vortices shift, magnetic fields twist and reconnect, the crusts crack and deform. Deep inside, matter that has been stable for eons is suddenly driven out of equilibrium. For a brief instant, the stars expose themselves. When contact finally occurs, the collision releases an immense burst of energy. Matter is squeezed, heated, and rearranged faster than it can respond. Densities rise, pressures spike, exotic phases that may have been confined to small cores spread outward, if only for milliseconds. This moment is precious. It is the only time when neutron star interiors are forced into new configurations rapidly enough to leave observable traces. The gravitational wave signal changes abruptly as the stars merge, encoding how matter responds to compression beyond its normal limits. Does the merged object briefly survive as a massive neutron star? Does it collapse immediately into a black hole? Does it oscillate, ring, and shed mass before disappearing? Each outcome tells a different story about the strength of matter inside. If the merged remnant survives for even a short time, it suggests that neutron matter, or quark matter, or something stranger, can support enormous mass under extreme conditions. If collapse is immediate, it implies a lower threshold, a softer interior, less resistance. In some events, astronomers observe not just gravitational waves, but light. Short gamma-ray bursts, colonovae, and afterglows accompany certain mergers. These electromagnetic signals arise from matter flung outward during the collision, rich in neutrons and heavy elements. As this material expands and decays, it glows, producing elements like gold and platinum. This matter comes from the outer layers of the stars, but its behavior is influenced by the core. The amount ejected, its speed, and its composition all depend on how the stars deform and disrupt one another, which again depends on their internal structure. In this way, even the aftermath carries echoes of the core. As you rest now, imagine the universe briefly holding its breath as two impossibly dense objects meet. No sound travels through space, no shockwave propagates through air, and yet, space-time itself vibrates, carrying the message outward. These vibrations are clean. They are not scattered or absorbed. They arrive at Earth nearly unchanged, bearing a faithful imprint of the collision that produced them. For physicists, this is a gift. Gravitational waves bypass many of the complications that plague traditional astronomy. They are not dimmed by dust. They are not altered by intervening matter. They speak directly from the heart of the event. From a single detection, scientists can estimate masses, spins, deformabilities, and sometimes even the radius of the neutron stars involved. Each parameter constrains what the stars could have been made of. Over time, with many detections, patterns emerge. Some equations of state predict stars that are too stiff, producing signals that do not match observations. Others predict stars that are too soft, collapsing too quickly. Gradually, entire families of theories are ruled out. This process is slow, but it is relentless. With each merger observed, the universe narrows its own possibilities. What makes these collisions especially powerful is that they push matter beyond its comfort zone. A neutron star in isolation exists in equilibrium. A merging neutron star does not. Its matter is forced to respond dynamically, revealing properties that would otherwise remain hidden. It is one thing to observe how a star behaves when left alone. It is another to see how it behaves when torn, twisted, and compressed by an equal. In those moments, matter reveals its true nature. The collisions also test the ultimate limits of stability. If a merged object survives briefly before collapsing, it suggests that rapid rotation and thermal pressure can temporarily support masses above the normal limit. This informs our understanding of how close neutron stars live to the edge of collapse. Some remnants may even pass through multiple phases in seconds, from neutron matter to quark matter, from stability to collapse, before disappearing. Each phase leaves its imprint on the gravitational wave signal, like a changing chord in a fading sound. We are only beginning to learn how to read these patterns. As detectors become more sensitive, future observations will reveal finer details. Subtle features in the waveforms may distinguish between different core compositions. Differences in post-merger oscillations may hint at exotic phases of matter. In time, we may even detect the moment when matter crosses a fundamental boundary, when a core transitions from one state to another under extreme stress. All of this happens far away, beyond any danger, beyond any reach. And yet, it reaches us. As you lie still now, it is worth reflecting on the gentleness of this exchange. The universe does not shout its secrets. It whispers them across billions of light years through vibrations smaller than atoms. Neutron-star collisions are among the most violent events known, and yet their messages arrive quietly, patiently, waiting to be noticed. They remind us that knowledge does not always come from control or proximity. Sometimes it comes from listening carefully to distant tremors and trusting that meaning is carried within them. As this chapter closes, one final thought lingers. If neutron stars reveal their secrets most clearly when they collide and disappear, what does that say about their place in the universe? They are not just endpoints of stellar evolution. They are messengers, brief, dense archives of extreme physics, whose final acts illuminate the deepest questions about matter, gravity, and time. And with that understanding, our journey begins to turn toward its final reflection, not on violence or collapse, but on the quiet perspective these stars offer. A reminder that even at the universe's most extreme edges, there is order, meaning, and a calm invitation to wonder. Part 15. The quietest extremes in nature. At the center of a neutron star, matter reaches limits not found anywhere else. It is a place where quantum mechanics, nuclear physics, and gravity meet in silence. No light escapes from within, no sound carries through its depths. Yet, its existence reshapes our understanding of what matter can become when the universe presses as hard as it possibly can. There is something deeply paradoxical about this. We tend to associate extremes with noise, with violence, with chaos. Explosions announce themselves, collisions scream across space, but the neutron star's core is different. Its extremity is defined not by motion, but by stillness. Everything that can happen has already happened. What remains is balance. The silence is not emptiness, it is fullness taken to its limit. Inside this core, matter is arranged so tightly that change itself slows. Particles are confined to narrow possibilities. Motion, when it exists, follows strict quantum rules. Nothing is free to wander. Nothing is allowed to waste energy. This is the universe in its most disciplined form. Every layer we have passed through on this journey has been a shedding of familiarity. Atoms disappeared, neutrons took their place. Then, even neutrons began to blur, giving way to possibilities like quark matter or strange matter. With each step inward, the rules became simpler and more absolute. At the center, only the deepest laws remain. Quantum mechanics dictates what particles may do. The strong force binds what remains bound. Gravity curves space-time into a shape that allows no escape from its influence. These forces do not compete here. They coexist, each operating at near maximum strength, locked into an uneasy but enduring agreement. This coexistence is rare. Elsewhere in the universe, these forces dominate in isolation. Quantum mechanics rules atoms. Gravity governs planets and stars. Nuclear forces act only in tiny spaces. In a neutron star's core, all of them matter at once, at full intensity. This is why neutron stars are so important. They are not just astronomical curiosities, they are testbeds for reality itself. They show us how nature behaves when pushed to the edge without breaking. As you rest now, imagine this place not as something hostile or terrifying, but as something calm and resolved. There is no struggle here, no drama. The star has already found its answer to gravity's demand. It holds, not because it wants to, but because it must. This quiet endurance carries meaning. It tells us that the universe does not always respond to pressure with destruction. Sometimes it responds with transformation, discovering new ways to exist within constraint. The neutron star is matter's final compromise, not free, not collapsed, but held in perfect tension. And this tension teaches us humility. Many of the concepts we rely on to describe the world fail here. Words like solid, liquid, particle, and even time lose clarity. They were never wrong, only limited. They were designed for gentler conditions. At the center of a neutron star, gentleness has been stripped away. What remains is not chaos, but order at a deeper level. Rules that do not bend, principles that do not negotiate, identity defined not by structure, but by necessity. In this sense, neutron stars remind us that the universe is capable of far more than our everyday experience suggests. The same matter that forms oceans, mountains, and living bodies can also become something utterly unrecognizable, and yet remain governed by the same underlying laws. This continuity is comforting. It means that even at the most extreme edges, reality remains coherent. It does not tear itself apart. It reorganizes. From far away, neutron stars look small, faint points of light, regular pulses, brief flashes, nothing about them suggests the extraordinary conditions hidden inside. This contrast is one of their quiet lessons. Not all depth announces itself. Some of the most profound truths in the universe are concealed within objects that barely draw attention. A neutron star's core contains more insight into matter than any laboratory on Earth, yet it sits silently, asking nothing of us. And still, we listen. We listen through pulses and waves, through timing and distortion, through the subtle ways space-time responds to their presence. From this listening, we build understanding, incomplete, evolving, but real. As this journey comes to rest, it may be comforting to let go of the need for final answers. Neutron stars do not offer closure, they offer perspective. They show us that matter has many ways to exist, that stability can arise under immense pressure, that silence can coexist with extremity. They remind us that the universe is not only vast but deep, layered with realities that reveal themselves only when conditions become extraordinary. As you lie here now, breathing slowly, consider the calm of this knowledge. Somewhere in the galaxy, a neutron star holds itself together against gravity's pull, quietly, patiently, without effort or sound. It does not rush, it does not burn, it simply is. And in that quiet existence, it expands our understanding of what the universe allows and what it asks of matter when it presses as hard as it possibly can. Let that thought settle gently. Because even at the very center of the densest objects known, the universe remains composed, lawful, and profoundly calm. And with that calm, our journey reaches its natural rest. As we come back from the heart of the neutron star, it helps to remember how small the distance really was, not in kilometers or light years, but in understanding. We did not travel outward across space. We traveled inward, through layers of matter, pressure, and law, until even familiar ideas began to soften. At the center of the densest objects known, we did not find chaos. We did not find noise. We found balance. Matter did not break. It adapted. Time did not stop. It slowed. Gravity did not destroy. It reshaped. Neutron stars remind us that the universe does not reserve its deepest truths for the largest things. Sometimes they are hidden inside the smallest, quietest remnants, objects barely wider than a city, yet heavier than the sun, carrying within them conditions that once filled the entire universe. And while we cannot touch these places, cannot see inside them, and cannot ever go there, they still reach us. Through steady pulses, through faint ripples in space-time, through the patient language of light and gravity. There is something comforting in that. It tells us that even the most extreme corners of reality remain connected to us, that nothing is truly isolated, that the same laws shaping the core of a neutron star are quietly shaping your breath right now, your weight against the yabar Earth, the slow passage of time as you rest. As you lie here, the universe continues its work. Stars burn, others collapse, some hold, some let go. And through it all, there's a deep consistency, a sense that reality, even under immense pressure, knows how to remain whole. If this quiet journey brought you a sense of calm, wonder, or gentle curiosity, I'm truly grateful you spent this time here. Your presence, your stillness, your listening matter more than you know. For now, there is nothing left to understand, nothing left to imagine, nothing left to hold on to. Just rest. The densest places in the universe are silent. And so is this moment. Good night.